Hey everyone, it's Miss B. In this video, we are looking at Unit 3, Lesson 6, Cumulative Practice Problems. And our first practice problem here is to define a sequence of rigid motions that will take A, B, C, D to E, F, G, H. So I'm going to write them down, but I'm also going to show you them. So I'm going to trace my shape here, see if I can get it kind of square. It's not entirely square, but it's close enough. The idea is that we want to move this here. We're probably going to end up rotating. So let's resize. If I rotate this, I'll rotate it so it'll line up. I'm probably going to have to reflect around here. A, B. Oh, no, I won't have to reflect, but either way, we're going to rotate it around, and then we are going to shrink it down using dilation with a scale factor to actually make it line up. So our first step is going to be, we're going to translate ABCD, and I'm going to say, so that A coincides with E. You could also say translate by the directed line segment AE. We just don't have one visible here, but that would still mean the same thing, that we would be going from A to E. So now, so let's actually, I don't know why I erased my first one. I'm going to draw my shape again, and then we will show you what I mean for each of these sort of transformations here. But I am going to label that these are A, because we want to make sure that all of our pieces line up. So I am going to include all of these. I'm going to rope them all in. And when we translate, we now have A lines up here. But we know that A corresponds with E, but B corresponds with F. And so A, B, C, D, this is going counterclockwise. E, F, G, H is still going counterclockwise. So we just need to make sure that we rotate until B lands on the one it corresponds with. So we are going to rotate until, let me move this out of the way for just a second. Well, actually, I'll just demonstrate it. We are going to rotate this. Now, technically, this is not rotating around a center. We want to rotate around center here until B. Now, it's not going to coincide because B is going to land way out there. But we can rotate by an angle that we either define and then scale it down, or we can scale it down and then rotate it. So either way, we'll end up where it lands up here, where B corresponds with F. So I think I might actually, let's scale this down first. So I am going to say that my next step is going to be dilate the image by a scale factor. Now, we actually have to figure out what scale factor we're going to use, and they did give us that we want it to be 2, but we're starting with 5. So in order to do that, we would need to figure out our scale factor, but we're going to use those two numbers. Normally, I would say you would use like the image over the pre-image, and in this case, that's 2 over 5. And that is actually the scale factor we're going to use. So I would say dilate the image by a scale factor of 2 over 5, but I also now have to provide a center of dilation. So I'm going to say using center, and I'm going to say E, because that was the one corner we had already made them line up at. So that will just take my big square that landed here and shrink it down so it's a little square, but still lands at this corner. Then I'll be able to swing it up and around into position. So that's going to be my third step, which is rotate the image around point E until B coincides with F. And that is a series of motions. Now, they're not necessarily rigid motions, all of them, so it does say rigid motions and dilations. The dilation there is in red, but my two blue ones are rigid motions. That brings us down to question 2. So question 2, we have quadrilaterals P and Q. They are similar. We want to know what is the scale factor of the dilation and what is the scale factor, well, the scale factor of the dilation that takes P to Q and then that takes Q to P. So if we are starting with P going to Q, that means that Q is our image and P is the pre-image. So if I have P to Q, that means I want a number from Q. So I want a number from Q to be divided by a number from P. So I am going to say, or I'm going to use just the numbers at the top, the 4 and the 5 for these makes the most sense to me. So I'm going to say 4, nope, in this case 5 is the one we have in the top, 5 over 4 for the first one. And then if we're saying it takes Q to P, that means we would use P as the image and Q as the pre-image. So this one would be 4 over 5. The scale factors that take shapes to each other like this are always going to be reciprocals. They're just going to be flipped over versions of each other. Okay, let's look at question 3. This just asks, what's our definition of similarity? So if two figures have the same angles, then they're similar? Not quite. If two figures have proportional side lengths, then they are similar? Also not quite. If there's a sequence of rigid motions taking one figure to another, then they are similar. Also not quite. D actually combines all of these. If there is a sequence of rigid transformations and dilations that take one figure to the other, then they are similar. And as a result, A and B will be true. They should have proportional side lengths and the same angles, but we're defining it using D. For question 4, we have triangle DEF, which is formed by connecting the midpoints of the different sides of the triangle. And they want to know what is the length of BC. So, length of BC is this whole side right here. So, that one is going to be parallel to DF. So that means I am going to use DF as my proportional side if I can now consider these kind of similar triangles. Because they are all going to be similar triangles, it's just something applied a dilation. So this is actually going to be the side length of EC and BE. Those would both be congruent to 4, so we're going to have 4 here and 4 here. Since this is really a scale factor of 2, you could also do this by taking the one that you know is the smaller piece, or the one it's parallel to, and multiplying that by 2 to represent that dilation by a scale factor of 2. Either way, it does mean that our answer is D. It is 8 units. Moving along, if we go to our next page, question 5 gives us another image, similar, that says, if AB is 12, what is the length of A prime B prime? So, AB is 12. They want to know what is the length of A prime B prime. Well, that is this one right here. So, we are going to use some proportions here, but because I don't know what this length is, I'm going to call this X for right now. And maybe I want to kind of think about this as 2 different triangles. I'm going to have the smaller triangle here, and then I'm going to have the larger one as the whole triangle. So I actually have to compare using a side of the entire larger part of the triangle, which is going to be 6 plus 3 here, which is really 9. So if my pattern of my equation that I'm going to set up here is something from my small triangle over something from my big triangle, and just making sure that I'm using corresponding parts, then I am going to be setting up the 6 and the 9 as the small and the larger parts, and then using x and 12. So I would say 6 over 9, and I'm going to say that's equal to x over 12, and then cross multiply here. So we would get 9x, and 12 times 6 is 72. And if we divide both sides here by 9, we would get that our distance is 8. So our answer here is 8. That brings us down to question 6 right here. A right angle ABC is taken by a dilation with center P and scale factor 1/2 to angle A prime, B prime, C prime. What is the measure of A prime, B prime, C prime? Well, you can't fool me. You were just talking about a dilation. This is 90 degrees. Dilations. We're going to say dilations preserve angle measure because they do not change it. They only change side lengths. So it's going to be the same. That brings us down to question 7. So using the figure to the right, got it, that's all on my screen, that's good. Using the figure to the right, we want to first dilate point C using center D and scale factor of 3/4, and then dilate segment AB using center D and a scale factor of 1/2. Okay, so let's start with the first one. Let's do C. So normally you would measure, and you would say, ah, yes, I see this length. Now, I'm not entirely sure what length this would be on your paper, and I'm not sure if I actually have a ruler. I can look in some of my tools here, but I'm not sure that I do. I think I have it on one of my other applications that I don't like as much, so in this case, we are going to estimate, because the whole point is that if we're dilating using center D and a scale factor that's smaller than 1, C is going to get closer to D. But is it going to move 3/4 of the distance? No. Its new distance is going to be 3/4. So if we're trying to imagine this, this would be half, and then half of half would be here. So that's right about where I'm going to put my point, and I'll call it C prime. Now, they want me to dilate segment AB using a scale factor of 1/2. And luckily enough, we can actually do that by just dilating the points themselves half the distance. So I'm going to do these ones in blue. A is going to go half the distance between itself and D, so this will be A prime. And B is also going to go half the distance. So I am looking at this distance here when I mark half, which is going to be right about there. So half the distance from B prime to D, or from B to D, makes B prime. So that is the result of our dilation. So I'm going to say C diagram, because that is how I answer this. Okay, and then we're almost done here. Question 8, a polygon has a perimeter of 12, and it is dilated with a scale factor of k, and the resulting image has a perimeter of 8. What is the scale factor? Well, we know that scale factors just affect the distance, so they're going to affect that perimeter, which means we can do the same thing we would with the shapes from the very first question in finding our scale factor. We're going to use the resulting, or the image, and divide it by the pre-image. So if it has a perimeter of 8, we're going to use 8, and that's going to be divided by 12. We're going to reduce this as far as possible, which means we would be able to divide both of these by 4, and it would reduce to 2 over 3. So this is a scale factor of 2/3, or B. But that's because it reduces, right? So divide by, here, I'll show my work, because it does say show how you got your answer. I'm reducing this by dividing them by 4 each. Okay, and then on to question 9, and this is our last question. We want to select all statements that must be true. And these are kind of our features of parallelograms and quadrilaterals. So, parallelograms have 4 congruent sides. Not necessarily. They can, but they don't have to. Both sets of opposite sides of a parallelogram are parallel and congruent. That will always be true. C, a trapezoid is a parallelogram. Nope, it cannot ever be a parallelogram. It will only have one set of parallel sides, and parallelograms have to have 2. Diagonals of a parallelogram bisect each other. This one is true and always will be true, but they are not necessarily congruent. Diagonals of a rectangle, and also a square, will be the only ones that are congruent. And that is it for the homework for tonight. So thank you for joining me for this video. This is Unit 3, Lesson 6, Cumulative Practice Problems for Illustrative Math Geometry.